Hi everyone, this is Maths for Uni. Today I'll be looking at the final part 3, of Step 2, 2019, Question 1. If you enjoyed this content, then please consider liking and subscribing, as well as checking out our full Udemy courses. The links are in the description. The question says, the tangent to C at the point with x equals c, where c is not equal to r, passes through the point r0. Show that this tangent is parallel to the tangent in part I if and only if the tangent to c at the point with x equals q does not meet the curve again. So notice that this part II is quite similar in how it begins with part I. We replace A by C and P by R. This means that we can immediately get a very similar condition to the 2A equals Q plus R that we found in part I. In particular, we have 2c as being equal to p plus q. We replace a by c, and we've replaced p by r. So in this one over here, p is missing, and so r is missing here, and we have p plus q. This is the information that we can gain from what we've been told in part II of the question. Now we need to show the if and only if. So we're looking at tangents being parallel to each other. In particular, the tangent in part I and the tangent in part II. If we look at their gradients, in particular in part I, we found minus a quarter a times r minus q all squared. Then in part II, we've replaced a by c and p by r. And so this will be minus a quarter times a p minus q all squared. So first, let's look at the parallel condition. So one direction of the if and only if. If the tangents are parallel, then we have that these two things here are equal. And this only happens because a is a non-zero constant if the squares themselves are equal. Again, this is because parallel for straight lines means that the gradients are equal. This has two possibilities. Either r minus q is equal to p minus q, or the other way around. R minus q is q minus p. This is because if we have, say, x squared being equal to y squared, then either x equals y or x equals minus y. You can see this by taking this over to the other side and then factorising in a difference of two squares, and you'll get this condition here or this condition here. The first possible condition, we can cancel the q's in, and so we get that r equals p. However, this is a contradiction because we were told that p is strictly less than q, which is strictly less than r. As a result, this is the only possibility which gives us the equation that 2q is equal to p plus r. Now, we want to show for this direction of the if and only if that if they are parallel, then we have that the tangent to C at the point with x equals q does not meet the curve again after it touches at Q. So let's write down the tangent to the curve C at x equals Q. From our earlier work in part 1 of these series of videos on question 1, we know that this has the form y equals, or rather y minus, q minus p g of q equals g of q plus q minus p g prime of q, and then we have an x minus q. This is specifically for g of x being a x minus q times x minus r, i.e. we have the specific case where we have taken out a factor of x minus p. For this particular g of x, we notice that g of q is equal to 0 because of this factor here. So this is equal to 0 and this is equal to 0, and therefore all we have is y as being equal to q minus p g prime of q times x minus q. Now, using the g of x that we have somewhere, yes, here, we can work out the g of, or rather, g prime of q. We have that g prime of q, based on some earlier work, is equal to a times 2q minus r, which is a times q minus r. So putting this into here, we get that the tangent to C at the point x equals q has equation y equals a q minus r q minus p times x minus q. This looks remarkably similar to the curve C itself. So we want to show that this tangent has no other intersections with the curve C. So let's intersect this tangent with the curve C. The curve C is essentially this, but with an x here, and so if we intersect them together and find the solutions, we have a q minus r q minus p x minus q as being equal to a x minus r x minus p x minus q. Now, we know that x equals q is an acceptable solution because this is where the tangent occurs. So x equals q is fine, and then we can discard that solution from both sides. And we can also discard the non-zero constant a, and so the other solutions to this equation must solve q minus r q minus p equals x minus r x minus p. We can see visually that x equals q will solve this equation again, because putting x equals q here and here gives the same thing on the left and the right. But because we have a quadratic, there may be another solution. So we should be careful to find both of these solutions. As such, let's expand out the quadratic and then solve. We have x squared minus r plus px, and then we have constants, which are, let's have a look, q minus r, q minus p, and then what do? We subtract off the rp from here and here. And so, therefore, this cancels with the rp from here, and so we get q squared minus r plus pq. q. Therefore, by moving some terms around, we have x squared minus q squared is equal to r plus px minus r plus pq. And we can factorize this as x minus q, x plus q equals r plus p times x minus q. So we have x minus q as a factor on both sides. Again, that's an acceptable solution because that's where the tangent actually crosses the curve C. And so if we discard x equals q again, then we have x plus q equals r plus p. So therefore, we have that x is equal to r plus p minus q is another solution. However, is this solution entirely distinct from the other solutions that we found so far, which are just repeated roots of x equals q? We've discarded two of these, once here, and let's have a look, once up here. Is this an entirely new solution? Well, if we have that 2q is equal to r plus p, which is the condition that we got up here from assuming that the tangents were parallel, well, what happens in this situation? R plus p minus q is 2q minus q, which is just q, i.e. there are no other solutions other than x equals q. As a result, we have shown that if the tangents are parallel between part 1, or rather part I, and part II, then the tangent to C at the point with x equals q does not meet the curve again. If we try and find their points of intersection, we just get x equals q as 3 repeated solutions. So there are no other places that they could possibly intersect. On the other hand, it's quite easy to do the other direction at this point. So now we assume that the tangent to C at the point x equals q does not meet the curve again. So tangent to C at x equals q does not meet curve C again, and then with this assumption, this tells us that this here must be equal to q. R plus p minus q must be equal to q, because if it's not, then we have another solution, which contradicts this assumption here. As a result, this tells us, by rearranging, that 2q is equal to r plus p. But then, if 2q is r plus p, then this here is true by rearranging, and then this here is true. And this tells us that the tangents are parallel. As a result, we have demonstrated the if and only if, which I'll just write as if and only if tick. This was the final part of the question that we wanted to look at, and we were careful to check both directions. If you found this content helpful, then please consider liking and subscribing, as well as checking out both of our Udemy courses, of which the links are in the description. Also be sure to check out our other step questions from Step 2 2019. And if you missed the earlier parts of this question, then Part 1 and Part 2 should also be available. Thanks for watching, and goodbye for now.